Hello everyone, and welcome to this presentation about engineering ecosystem models. The authors are Tristan Caulfield, Marius-Constantin Ilau, and David Pym. I'm Marius-Constantin Ilau, and today I'll try to give everybody some ideas about why thinking ahead about modeling ecosystems is important. Given the relatively small amount of time, I'll attempt to describe our primary goals and motivation, spend a bit of time on our interpretation about the nature of models, describe the main components and operations available in our modeling framework, and then provide an example of a real model having been implemented using a Julia implementation of our abstract modeling framework. As a small disclaimer, I'll not attempt to present any formal proofs, since those can be found in the actual paper, and I'd probably end up taking for 20 minutes without managing to describe even half of them. Starting with the actual goals, our primary one is to construct a semantically rigorous approach to modeling that would manage to capture the semantic structure of ecosystems and which could then serve as a theoretical basis for the construction of tools for reasoning about models and constructing them. However, before diving into the actual framework, we take some time to list some properties we believe of great importance for a modern modeling framework and which are achieved by our attempt. Firstly, a modeling framework should be generic enough to represent the complexity of ecosystems without an epistemic bias towards a certain modeling tradition. Secondly, it should be both modular and scale-free to facilitate parallel work on disparate components, no matter the underlying complexity of the model system. Thirdly, it should facilitate the complexity management of the underlying system without the introduction of synthetic notions that do not relate to the system. And lastly, it should be easy to use in practice, easy to understand, and provide the ability to reason about model subcomponents in isolation without the need to reason about the whole system. Therefore, one essential aspect of our modeling approach is that it is based on a small set of components and operations. Now, some might ask, why is this new construction necessary? To use a somehow similar example to Moore's law, systems complexity increase over time, sometimes because of poor design choices, or simply because the sheer magnitude of their operations. However, as the idiom says, the map is not the territory, and complex system doesn't necessarily have to mean complex models. Therefore, our main concern is to produce simple models that facilitate understanding and action. Furthermore, the complexity of social technical systems leads to inherently multidisciplinary phenomena to be modeled, and the best way of approaching this is using heterogeneous models that combine research tradition and epistemic assumptions. A less generic approach would introduce even more complexity into the representations and would be hard to use for reasoning about phenomena not specific to that tradition. For example, using traditional systemic dynamics to reason about user behavior or conceptual psychologically inspired models to predict the lifespan of a car's engine would be a somehow curious decision in my personal opinion. Nonetheless, when modeling the interaction of autonomous vehicles with non-autonomous vehicles, pedestrians, or road infrastructure, both the conceptual and system dynamic approaches could be used in composition. Following our desire for simplicity and generality, we view models as representation of phenomena performed by certain entities that manifest relationships between them. They can be used for understanding, learning, predicting, testing scientific theories, perhaps even entertainment if we think about a certain truck driving simulation engine that has been very popular in the latest year. Long story short, they have many uses. Based on their construction technique, knowledge types used, and language, we describe models as having a certain degree of conceptuality, mathematicality, and executability. A very conceptual model would be, for example, a framework for business policy construction, described in natural language or drawn. A very mathematical model will be, on the other hand, describe a phenomenon using formulae and equations. For example, you can see in physics Newton's laws. For more information regarding this, we have a separate presentation that focuses specifically on modeling traditions and combinations of them. Now, to finally get to the ecosystems, we view them as systems of various types. For a more precise definition, the information systems literature defines them as multiple aggregated supply and demand markets depending on each other. Traditional examples are the PlayStation or Google stores, infrastructures, transport networks, and others. Getting into the actual framework, we started from the metaphor of a distributed system as viewed in computer science. The key notions are of locations, resources, processes, environments, and interfaces, followed by a set of operations, including composition, substitution, and local reasoning, to support our original goals. In the figure below, we can observe three composed models and an isolated model. The white boxes represent locations, the arrows represent processes, the interrupted line encompassing two locations in the process is an interface, and everything is surrounded by the environment. Starting with locations, they simply represent the places where resources reside. They can be physical, for example a room, logical, such as an address in computer memory, or abstract, for example the location where a certain semaphore exists without any extra information because that might be relevant to the modeling goal. Furthermore, such locations need to be connected to allow the movement of resources. Because of this, we have chosen to formalize them using directed graphs. Going further, we have the resources, which are the components of systems that are manipulated by processes. They exist at locations and can move between them based on their connections. In practice, they can be physical objects, people, information, or simply anything viewed as a resource in the context of the model system. Formally, we have chosen the structure of an ordered, partial, and commutative monoid for them. Next, we have processes, which represent the dynamics of the system. Practically, they are the actions performed on resources at certain locations. We formalize them using a monoid of actions that support composition and the grammar of process terms that can be seen below. Using these notions, we can then describe a system's evolution over time as the coevolution of locations, resources, and processes under a generic action A. Then, we have the environments, capturing the world outside the system. They are parts of the model, relevant enough to be included in the model, but without the same level of detail. They cause certain events to happen, for example, using a negative exponential distribution on an empirical basis to capture the arrival rate of employees to a building. An interesting property is that they can be substituted with other models to increase the level of detail. Formally, they associate located actions to probability distributions, as we can see below. However, none of the previously described notions would allow the construction of compositional, modular models without interfaces. Interfaces connect models with other models or models and environments. They represent locations where models fit together and which actions are part of the composition. We formalize them using a tuple of input-output vertices labeled with resources and a list of located actions. An important point to make is that even if bounded by a computer science tradition, they essentially facilitate the composition of models with different epistemic assumptions. Using the previously described notions, we can finally define models as tuples containing a location graph with labeled resources, a set of actions, a set of processes, a set of located actions, and a set of interfaces. Associated with this mathematical structure, we are using a Hennessy-Milner-style logic where propositions assert properties of system states. More details about it can be found in the actual paper. Nevertheless, we have chosen this structure because it allows the thorough definition of composition, substitution, and local reasoning, which can be observed in the figures below. In the first diagram, we can observe two models, M1 and M2, in an environment N, and composed initially with a model P and then with another Q. Composition is allowed if the model P and Q satisfy the contracts provided at the interface I1 and I2 and J1 and J2. In this case, if the interfaces I1 and J1 and I2 and J2 require similar locations and located actions, the model P and Q can be substituted. In the second diagram, we observe a model composed with three environments or another models. We can view this as a country's map, with the black dot representing a city and the arrows representing the roads used to get into the city. To substitute this city model with a different city, we would have to satisfy the condition of its interfaces, which in our case is that the number of roads going in and out of the city is the same. However, knowing the arrival rates given by the negatives distributions, we could reason locally about events in our city without taking into account the complete map. This serves a dual purpose. Firstly, it's a powerful optimization because it greatly reduces the model space, while at the same time conserving assurance because of the underlying mathematical structure. Last but not least, we briefly present the architecture of a practical model used for experimentation with different organizational recovery techniques under ransomware attacks. This model will be presented in a further paper at the same conference. The model is actually a composition of three different ones: a server model, a network model, and a device model. The server contains operating system images as resources in a server location. The network model hides the complexity of network traffic routing, and the devices model contains the locations and devices requiring an OSIM re-imaging. The main goal is to determine a good configuration of recovery techniques that would lead to reduced network congestion given a distribution of malware attacks. We can see below a simple representation of how such a model would look like. As seen, devices send requests over the network. We can see this even better on the right side because that's the actual diagram of the implemented model. So, the devices send requests over the network to obtain new OS images from the server when hit by malware. We cannot see any explicit malware module because that would be a too great level of detail. We only need to know when devices get hit. However, in the second diagram, we observe the actual architecture of the Julia implemented model with a greater level of detail. For the practical stochastical experimentation, the second might be required, but in certain cases, reasoning about the system can be done only using the first diagram, so it's not only that we have to implement our models in software code for them to be useful, at least for reasoning in certain situations. Although already in a functional state, much additional work can be done. One possible area could be about the development of verification and validation tools that would take into account the stochastic aspect of our framework. Secondly, we realized that more experimentation with the framework should be done, particularly in non-technical contexts. Lastly, we realized that the framework could be used as a basis for a methodology of model design and construction specifically focused on heterogeneous models, so we intend to work on these three different areas in the future. Thank you very much for your time.